Classical Physics Tutoring, Chapter 5, Section 2, Magnetic Field Equations. Okay, so we cover magnetic field here. There's a lot of things to cover. So some of equation derivation of equations we made other videos, so you have to look at other video because otherwise this typically like 2 weeks of lecturing we shorten into less than 30 minutes video. So magnetic field is generated by what? There are two sources of magnetic field, which is magnetic charge and the current, and that's you're going to learn later in this section, the Maxwell's equation. Now the magnetic field, just like electric field, we have electric field and the flux. We have same way magnetic field and magnetic flux. Okay, the way magnetic flux is generated, there's only two way we have, and both of way generate magnetic flux as a complete circle. Okay, like the current, magnetic flux generated around the current as a circle, and magnetic charge is also they generate the flux as a circle. From here, positive magnetic charge to negative, and here's a magnetic dipole, which is magnetization, and B equals mu H, and the mu contain this M, right? Mu equals mu 0 plus mu 0 1 plus susceptibility. So that's include this. So the magnetic flux actually is going to circle around, but do not get confused that magnetic field goes from positive magnetic charge to negative magnetic charge. So within the magnet, the H and B, flux and magnetic field, is opposite usually. Okay, and we get into this later, but do not get confused. But all the equations same as the dielectric, whatever you learned in the previous video, except, okay, this magnetic charge is like the surface charge generated by dipole in the electric field going through the dielectric material. So the origin of E can be just single electron or the true charge, which doesn't exist in the magnet, and that's gonna induce the surface charge on the dielectric material. Magnetic material also, say if you have magnetic field, then the charge is induced, right? The difference, what's the difference? The difference is most of dielectric material, when you remove electric field, then surface induced charge disappear. But magnetic field, some material, so the hard magnetization, after you remove this H, the surface charge still remaining, and that's generate magnetic potential and magnetic field, just like this. That's the permanent magnet. So we don't have such a things like permanent dielectric material which has a charge on the surface. Well, there may be some, just the degree, but the magnet, we have very strong surface material, surface charge remaining and act as a permanent magnet. Okay, so pretty much all equations same, except there's no true magnetic charge, only the surface charge by dipole created. So since B flux is circle, always closed circle, you take any closed 3D area and calculate the divergent. B is 0 because in and out balance out, right? Okay, I hope you learned this in the vector calculus. Now, same way, magnetic field generated by this magnetic charge is negative gradient and magnetic potential. So magnetic field also is related to magnetic potential. So you have a electric field, electric potential, and magnetic field, magnetic potential. So this relation is same, and same Gauss law apply for this. Okay, so when you removed magnetic field, some materials stay magnetized, and we talk about that mechanism a little bit here. Before that, let's fix some terminology. Okay, the magnetic flux is measured by Weber. Okay, and density is Tesla. Tesla is Weber per square meter. And 1 Tesla, 1 Gauss is 10,000 Tesla. Okay, now we have many different way to define the amount of magnet, the different unit. Well, the reason is theoretical work to make a formula clean is not necessarily convenient for experiment, because the magnetic field is so strong in the formula. It's not easy to make it in the experiment. Experiment use much weaker magnetic field. Generally speaking, magnetic field produce the huge force. Okay, so the theory and the experiment kind of use a different unit, and using this Gauss is much easier to express the formula, but the measurement use like Tesla. Okay, so magnetic field has the same coefficient permeability in the vacuum, which is corresponding to this, and susceptibility, which is dipole, is generated by magnetic field, just like the dipole is generated by electric field, right? So same equation stands here. Okay, so exactly same way, mu is defined as mu 0 1 plus chi. So this is the magnet constant, and This is the relative magnetization constant. We come back to this later. So what happened is flux is usually, if there's no current generating magnet, only permanent magnet, the magnetic flux becomes negative dipole, this opposite direction, because M is generated by H, and M is opposite to flux. Okay, so equation, you divide this flux caused by surface charge and real charge, then you get this equals this equation. So this is same as D equals E. Okay, exactly corresponding. It's a symmetric. So all the stuff you learned in the dielectric material, you can use it in magnetic field based on permanent magnet. Okay, so we already said this, and this is the definition, and this is the relationship. So the constant is also corresponding. Let's clarify. This is the vacuum permeability. They call this vacuum permittibility. And this is a relative permeability, S, and this is a relative permittibility, and combine this together, you create the magnetic permeability, and we call that dielectric permeability, or sometimes dielectric constant. It's historically is dielectric constant. The later the name has been made it consistent. So this is a magnetic susceptibility, and this is dielectric susceptibility. This is the ratio, how much dipoles are generated by the field. Okay, so we already learned this in the previous video. You can go back and review. Exactly the same things happen. The mechanism of magnetizing the magnetic material is, when you have a H, every magnetic material has tiny magnet. This is a molecule, but its orientation is random. The overall, you don't see any magnetization. But once you apply H, this spin, each arrow spin realign with H. It depends on material. Okay, and material, we have like paramagnetic, means it's generated opposite. When H goes here, it's called surface magnetization become opposite. Like ferromagnetism, it's like very big amount of polarization happen. Okay, and now when you remove H, what's happened is this happened in the soft magnetization material. Means when H is removed, polarization come back. Okay, so there's no magnetization no more after H is removed. But the fellow magnetic material, after you remove, you have this much dipole left. Okay, in order to remove that, you have to magnetize in the opposite direction and come back. Then you have opposite side. Okay, so this is the magnetic, this is a memory effect called. Remember, it's magnetized once, and this is called hard magnetization, and this loop is called hysteresis loop. So this kind of material used in the recording material, that means say you have a tape and this kind of magnetic material is sprayed in a thin layer, and the signal come and magnetic field applied, and 0101. Okay, then this can be the opposite direction, so it's magnetized this way and this way. So later you have a magnetic field sensor scan this, then it can recover 1101. Okay, but this kind of magnetic material used for memory a lot in the past. Right now it's a semiconductor memories. How to erase this? Okay, when you have a hysteresis loop, what they do is they apply magnetic field, and the second time apply a little bit less, and a little bit less, and a little bit less, and that's a way to erase magnetic memory. Okay, so this is the mechanism of making permanent magnet. Now the so far the theory of magnetic field is caused by dipole, and exactly same. It's apply Gauss law, and also the Poisson's equation, the same thing. Please check the previous video for electric field. Okay, we get exactly same formula, and if it's a symmetric sphere, we get this equation, and this is the Poisson's solution. Actually, it's an integral form of Poisson's equation integral form. Okay, so we don't repeat the same theory here. It's just, since the basic all symmetric, apply same thing. Okay, now for example, see, you have a magnetic stick. This side has M plus and M minus. That's going to generate magnetic field. If you look at this, is a Poisson's formula, and we use this formula to find out what kind of magnetic field we get. So actually we can calculate, take an integral after you select the coordinate properly. Okay, and this exercise you can look at the details. And what the problem here is, it tells you take a gradient to see what kind of H you're getting it. The H is running this way from positive to negative, but this is a magnetic stick inside. The B flux is making a loop, complete loop. Okay, so what's happened is this M is negative of H. It's go against the polarization. So the M is looking at this way, and H is applying this way within the stick. So it's going to be naturally demagnetized. Over the time, all the magnetic stick is going to be demagnetized because of the magnetic field generated by itself. And this is not good if you want to keep the magnet strong. So what you do is, if you have a stick, you attach magnetic material this way. This is N, north, and this south. Then all the magnetic field goes through here instead of inside the magnetic stick itself. So inside H become very tiny, and demagnetization effect become minimum. Okay, when you have this horseshoes magnet, usually you put the iron plate. So the magnetic field doesn't run within the stick, it's all run here. Okay, and this iron stick get magnetized, but it's avoid demagnetization. Okay, so you can go through this exercise and you can check the direction of the H produced by the surface charge, and you see that go against the magnetization. Okay, this is this kind of interesting phenomenon. The people don't know why they always the magnet come with iron piece attached. There is a reason. That's a way to keep the magnetic power longer. Okay. So there's another way to generate the magnetic field, which is the current. And the current density convention is I is the current, J is the current density. That means amp per square meter. This is amp. Current generate magnetic field. So how it's generated? We have a, what is that? Oh, this equation. Okay, the vector rotation or curl, and typically when you say A equals curl B, then the relationship is, remember this, A and the B is vector is circling around. That's why it's called curl. Okay, not opposite. Okay, and this is direction of curling is the right hand screw. Okay, so you have a I, then B is generated this direction, and that's the curl effect. So the Maxwell's Amperes laws, Ampere originally find out the current generate the magnetic field, and Maxwell formulated nicely using math. Okay, it's good to be good at math, right? So the current, this is the integral form. They are same thing, it's just a different form. Integral form look like this. That means you integrate the B along this line, same as the integrate all the current within this circle. Okay, now there is another, Ampere didn't address this, but Maxwell addressed this. Another type of current that also generates magnetic field. What kind of current? It's called displacement current. And displacement current is the change of d flux. And when it happens, when you apply alternate voltage source to the capacitor, then the current flow, although they are not connected. The reason is you charge up, and next moment you discharge and go to opposite, and next moment you repeat that. So the AC means the time variant of d flux. The circuit is almost same as having current, okay, alternate current. So actually the Maxwell Amperes law have this term, displacement current, on top of the steady current density have a curl B. That means even there's no net electron moving through, this count as a current. Okay, so here's a formula you use often. How much magnetic force, okay, since the dB is generated by this formula, it's just integral form. If you put magnetic charge here, you can calculate a force. That's a force, right? But this doesn't come alone, usually come with negative. So it's always moment. You put magnetic stick here, then it's spin. So what kind of torque it's going to receive? And that's a kind of exercise. I made this other videos, exercise problem, and you should go ahead look at that. So next one is Maxwell Faraday's law. And what it is say you move magnetic field around this conductor, then you generate the current. Well, actually what you generate is electric field, and equation look like this. The amount of V flux within the circle you integrate, and that change is going to cause the internal voltage, which is line integral of electric field. Okay, so now this one, the interesting fact about this formula is you can go through a little bit more details. You move V and conductor is fixed, or conductors say spinning and the B is fixed. It doesn't matter, only the change of V. Okay, when you take an integral, it's sometimes the conductor moving or B is changing. You have to take both changes at the same time. Okay, so again, I made this another video, the detail for this Maxwell Faraday's law. I think you should review that. Look at the video. And now the last topic is this. You may wonder, okay, the current to generate magnetic field. Magnetic field change generate the current. Ultimately, E causes the current. So it's kind of feedback loop, right? So which direction is feedback? It's a negative feedback. That means the system of electromagnetic field is resist the change. So what's happened is, remember this, when you try to change something, you need a great effort, and that's, you need energy to do the work. Okay, so you combine two formula, the Maxwell Amperes and Maxwell Faraday's law, you will see it's negative feedback. You try to change something, it's resist to the change, and resisting a change means you need a great effort to make a change. That's the energy is injected to make a change. Okay, I hope you enjoyed this video, we talk about the field energy from next section, next video. If you like, please subscribe.